Okay, that's good. How far did we get? Did anyone get up to C? D? Anyone did E? One person? Anyone get to F? We got to F? We're doing oh, but you were here like way earlier.
Yeah.
I remember, yeah, you got here like 15 minutes earlier or something. Okay. Let's actually make sure that everyone knows how to do this. Start with A. Limit as x approaches 1. Okay, what do we do here? Yeah?
You can just plug in 1.
Done, that easy. Plug in step 1, right? Step 1 is to plug in. Okay, B. What do we do here? Yeah.
Simplify then plug in. So
Okay, what is
You're
it
gonna-
simple to?
so 1 plus x, 1 minus x, and then you're gonna have to take out a negative from the like the 1 minus x.
Factor out a negative out here.
Yeah. And you'd flip around. So those cancel. Insert the negative on the bottom.
Yeah. And then?
So you'd insert the negative and then also plug in, so
And then you can plug in, and we get what?
negative 1 out.
Minus a half. Is that one? Which is step 2 in the strategy, right? So step 1 was plug in. If that's your answer, if that works out, great, that's the answer. Step 2, if you can't plug in, which here we can because we divide by 0, we plug in a 1 for x, try to simplify to see if you can plug in. And that actually works here. Or it's C, limit x goes to 1. What happens here? Yeah?
You can simplify it to x plus 1 divided by x plus 1 times x minus 1.
Cancels. So what do we have now?
From there, I started, I tried plugging in 1 and that did not work, so I made a table
Right.
of values.
Okay.
And I got that from the values I used were 0.9, 0.99, and 0.9999, and then 1.00, 1.01, and 1.1.
0.9, 0.99,
Yeah.
0.999,
And then
1.
1.001, 1.01, and 1.1.
Okay. What did you notice?
I noticed that all the 0.9s kept approaching negative infinity, while the 0.1s were approaching positive infinity.
Right, so these here kept getting smaller, while those kept getting bigger.
Mhm.
I'm not gonna plug, that's kind of annoying actually. A nicer way, which is almost equivalent, is to actually draw the graph. What would the graph of this look like?
You would have, I don't remember the exact terminology, but you would have, it would be always approaching zero, never hitting it, going more up on the first quadrant, and the third quadrant will be always approaching. And infinity as it gets closer to the y-axis.
For this one? 1 over x minus 1?
Other way around.
I
didn't draw
So
the
I think the graph you were thinking of is
Yeah, I'm-
like 1 over x
Yeah.
is this,
Right,
right?
yeah.
So
it'd
if
be
you have
like
1 over x minus 1,
over.
what
It
happens?
would be over one more.
Huh?
You shift it
It's a shift where?
Yeah.
to the right.
Right, you shift to the right. So at 1 happens where what happened at 0 before now happens at 1. And so it's like that. So now based on this graph, what can you say? Limit as we approach 1. Does not exist. Because there's disagreement. On one side it goes to infinity, on the other side it goes to negative infinity. What if I had done this? And actually that problem instead. A little minus sign here. Yeah?
It would have been negative.
Negative infinity, because that just means from the left, so you don't care about this side. Okay? But without that, it actually does not exist. Illustrates the next point. Sometimes you can't plug in, so you simplify to try to plug in, but even that doesn't work. Then try a graph or a table of values. For something simple, I'd probably try the graph first, because without a calculator, even plugging in a table of values can be really annoying. Let's move on. Okay, so D. What happens here? Yeah?
So x is 0, so the absolute value of x is gonna be 0.
Okay,
So it's gonna be 0 over 0,
okay,
which is gonna give you 0.
no.
No.
You cannot divide by 0.
Oh.
It's never okay. The x in the bottom makes that, yeah.
Well, I made like a table and a graph, and it showed that like it doesn't hit 0, so that just makes sense.
What does your graph look like?
It's 2 lines, like, but they never touch.
Okay.
A closed circle,
Like which lines?
like straight lines. One going to the right, one to the left.
And what do they look like?
Like, there's no slope, like it's just 0, like it's just a slope in there.
Horizontal line?
No, vertical. I mean, yeah, sorry, horizontal, yeah.
Where is it on? Where do
At x equals 1, I mean, at y equals 1, yeah.
like that?
Yeah,
And then -1, like that? What happens on the y-axis?
it doesn't touch.
So how do you write that on the graph?
Over the hole.
Circle here. Circle. That's actually the correct graph. How do you figure that out, or how do you even know that? One way is to actually try to remember, what does the absolute value of x mean? What does that mean? When someone's right, the absolute value of x, what do you think? Yeah?
It means even if x is a negative value, it's always going to be the positive of that number.
Okay.
Do you want an
How
example?
does that help you put it in a calculation of like?
The numerator is always going to be positive.
Not really.
When x is less than 0, x is equal to x. When x is equal to 0, x is 0. And then when x is less than 0, x is negative.
Well,
Right.
not quite. I think you kind of mixed up there, but
The-
I
wait, the
know what
first
you're
one
saying.
is,
It's x
when x
if
is
your
greater
x
than
is
0.
positive.
Yeah.
It's negative x if your x is negative, and it's 0 if your x is 0. This is the definition of the absolute value of x. Yes, it means that it'll always, whatever you put inside it, it will always return 0 or a positive number, but you knowing that doesn't really help you with calculations. Remembering it this way would. And so If you had like the absolute value of 3, well, that's just 3, because 3 is bigger than 0, so it just doesn't do anything. If you have the absolute value of negative 3, well, that's negative, so it takes the negative of it, the negative of negative 3, makes it positive 3. Right? And of course, the absolute value of 0 is 0. Right? So that actually tells you how to deal with the absolute value of anything. Now, that being said, once you have that idea, and of course, you should know what the graph of this looks like. So that's just like at 0, it's the output is 0, and then it's like a V. Because on this side, it's y equals x. And on that side, it's y equals minus x. Which means, if I see the absolute value, it's approaching 0, I know on the left and the right is going to do something different. How do I show that in calculations? Well, I know that if I'm looking at it from the right side, the absolute value of x is just going to give me x. Whereas if I'm looking at it from the left side, the absolute value of x is going to give me negative x. And in this case, at 0, well, this gives me gibberish. Can't divide by 0. It doesn't make any sense. So, what you'll notice then is this can be simplified. And you could put the little plus sign and a little minus sign here, but once you do this, I'll know what you're talking about. X over x is just 1. If your x is greater than 0 and your minus x over x is minus 1. Your x is less than 0. So your function actually behaves like 1 on the right side, just a horizontal line y equals 1. Behaves like minus 1 on the left side. And you can figure that out by knowing the definition. So now that we know what the graph looks like, what's the answer?
Does
Yeah.
not exist.
The end. What if I put a little plus sign in?
One.
Would be 1. With a little minus sign, it would have been negative 1. Without anything, it does not exist, because on the right side and the left side, it's doing something different. Let's do E. Ideas. Yeah?
Can you just plug in 0?
Can you?
I
If I plug in 0, that's gone,
So it's square root of 1 minus 1.
right?
in the
Square root of 1
denominator.
is?
It's gonna be, oh, is it 1? Sorry, I didn't know
Square
that
root of 1
rule.
is 1. So
Okay.
you'd actually divide by 0 by plugging in, so plugging in directly does not work. Other ideas? So plugging in doesn't work. Next thing to try is to simplify so that we can plug in. Can this be simplified somehow? Yeah?
You could change the radical to a half, but that's the only thing I think of.
Yeah, that's rewriting and not really simplifying. Any other ideas? You have an idea?
Can't you like multiply the top and bottom?
By what?
The reciprocal, like the square root of 1 minus 3x? Something like
Not quite,
Wait.
but almost. Anyone?
I
Yeah.
think she's talking about rationalizing it.
Rationalizing. You can rationalize the denominator by multiplying by
the radical of 1 plus 3x plus 1.
And then,
And then you multiply the denominator by the same thing.
right, so you're multiplying by 1, essentially. But you're multiplying by 1 in a way that's very convenient. This is called rationalizing. What is this thing called here? What's the name for that thing? You remember? It's called the conjugate. In fact, it's the conjugate of 1 plus 3x minus 1. You can multiply and divide by the conjugate, and that can help us simplify. Now, word of warning, what you don't want to do, one of my morning classes suggested, you guys are also in my morning class section. Warning, common mistake here. Some of you can probably guess what I'm going to say, because some of you probably even thought about it. You cannot square the top and bottom. Some of you might have seen that radical, oh, can we just square it? No, you cannot square it. Right? Like if I give you a fraction, and then you just randomly square the top and the bottom, you change the value of the fraction. You can't do that. Right? So you can't just go in and square everything just because you feel like squaring it, just to get rid of a radical. So if you thought about that, can't do it. Illegal. Right? If you have an equation, you can square both sides, and that has some repercussions. It's not illegal. Right? If I give you a fraction, you just randomly square top and bottom, that's illegal. No. No bueno. To simplify this one, you would multiply and divide by the conjugate. Now what that does, if you're paying attention in the denominator, you'll notice that it now looks like a minus b times a plus b, which multiplies out to be what? A minus b times a plus b.
1 plus 3x plus 1.
Well, no, this specifically.
A squared plus 2.
A squared?
Plus 2ab
No.
plus ab.
A minus b times a plus b. Yeah?
A squared minus b squared.
Right, it's difference of squares form. A squared minus b squared. Right? So that allows you to get a square in there without actually doing anything illegal, like just randomly square. Right? So now you'll realize what happens to the denominator. It's just going to become the a squared, which is 1 plus 3x, minus the b squared, which is 1. And in the top, well, nothing really to do there, I'll just multiply it across. And now you'll notice what happens. 1 minus 1, those guys would cancel. So it's simplified. I mean, it still looks a little bit scary, but that's simplified. What can we do now?
Cancel an x.
Cancel the x, simplify further. It's not fully simplified, but we can cancel now. So I end up with the limit as x approaches 0 of 1 plus 3x plus 1 all over 3. And what's that?
Two-thirds.
2/3. So that limit is actually 2/3. That was EF.
can we just say it's 0 because the denominator's exponent of 5 is bigger than the exponent of 3 on the top?
Yeah. 0. Yes, nothing in the right here. What you could say is it's bottom heavy. Because, yes, you can look at the highest power on the top, that's an x cubed, and the highest power on the bottom, that's an x to the 5th. The denominator overwhelms the numerator. X to the 5th is way bigger than x cubed as you're going off to infinity. And so the denominator gets huge while the numerator stays relatively small. Such a fraction goes off to 0. Now, of course, step 1 can't work because you can't plug in infinity, which means step 2 can't work because you can't simplify and plug in infinity. Table of values or graph, forget about it. I'm not even going to try. But that actually works, yeah.
Is there like, see how like on the bottom it's like negative 3x squared? Like, is there ever an instance where like, whatever, like.
No, that won't matter.
It won't matter.
So now, for me in this class, that's good enough. Like you write 0 because it's bottom heavy, I'm fine. You've shown your work, that's the answer. Let's look at y. And it'll also answer your question, why the minus 3x squared is going to matter. Why does that actually end up being 0? So the trick, I guess, not a trick, but when you say, well, there's a trick or there's a secret, everyone pays attention. So the trick is to divide top and bottom by the highest x power in the denominator. Always the denominator. And when you do that, you'll see what's going to happen here. So you can go through, highest power in the denominator is x to the 5th. So you just go through and you divide everybody by x to the 5th. Simplify a little bit, that's just 4 over x to the 5th. The x's cancel here, that's 1 over x to the 4th, minus 1 over x squared, over 2 minus 3 over x cubed, plus pi over x to the 4th, plus radical 2 over x to the 5th. Now what you notice is each of these guys over here, they're fractions where the numerator is a constant and the denominator is a variable growing to infinity. So what's going to happen is all of these guys are going to keep getting smaller and smaller and smaller. They're going to go off to 0. The graphs, we know 1 over x squared and x fourth, 1 over x to the 5th, they all taper off like that. All of these guys just go off to 0 because the top is constant, the denominator is moving and growing. So essentially what you end up having is 0 over 2, which is 0. Okay? And that's why it's 0. So essentially, because you divide by the largest power in the denominator, none of the lower powers, any power that's lower than x to the 5th is not going to matter. They're just going to vanish. They're going to go off to 0. So you don't care about this or that or that or that or that. Right? The highest power is going to control what's happening. Right? And so 0. But like I said, you don't have to show this. Just writing, oh, that's 0 because it's the bottom head. I'll assume you know what you're talking about. As long as you say at the correct time. G This is for this one? Yeah?
Because since you're going down to negative infinity, it means that any cube, like any odd power to that is going to be consistently negative, making you have some form of positive infinity at the top that's much greater than the negative infinity on the bottom. because x to the fifth is much greater than x to the cubed. However, since you have a positive over a negative, you'll be going down to negative infinity.
So, negative infinity.
Yes.
Why? Because it's top heavy. Now, also, more algebraic, you can actually do the same trick to see that this would be the case. And basically, if I go through and I divide top and bottom by the highest power of x in the denominator, that'll be 4 of x cubed minus 6x squared over 7 over x cubed plus 2. Divide top and bottom by highest power in denominator. You will obtain that. You will notice again that these two guys go off to 0, which means pretty much the only thing of concern is going to be the minus 6x squared and the 2. Now, of course, the top is going off to infinity, and you're dividing by 2, so it's still going to be infinity. The only thing that you have to worry about here is the sign, which infinity, plus or minus infinity. Well, by negative infinity into the square, that becomes positive. You multiply by a negative, that's negative, then you divide by a positive, so it stays negative, and that gives you the negative infinity. And so that's why there's a negative sign. So that would give you negative infinity. Because the top is overwhelming the bottom, we call that top heavy. H. This is on this one.
Is it top heavy again?
Is it? What is the highest power on top?
X to the x cubed, but it's
It's
the
x
same
cubed,
as well.
17x cubed.
Yeah,
Right, so what's the biggest guy on the bottom?
negative 2x cubed.
2x cubed. So you said it was top heavy?
I'm not sure.
Can you use that like same rule and just look at the 17 and the negative 2 and know that it's gonna be negative, and so it's negative infinity?
Well, if we were to use the same rule, what would happen? Right, like if we use the same trick, right? So I'm gonna divide the top and bottom by x cubed, that's the largest part of the denominator. So this divided by x cubed gives me 17, this divided by x cubed gives me 3 over x, this divided by x cubed gives me 1 over x cubed, this divided by x cubed, 5 over x cubed, this divided by x cubed, 1 over x squared, this divided by x cubed, you get minus 2. These guys are going to go off to zeros. And what are we actually left with?
17 over negative 2.
Just 17 over negative 2. There's no infinity to speak of. Negative 17 over 2.
So that's just the answer.
That's the answer.
Oh,
What you can notice here is that, remember in a polynomial, the term with the highest power, that's called the leading term. The coefficient of that term is called the leading coefficient. And I just took the ratio of the leading coefficients. And so, of course, math people were awesome at naming things very cleverly. This is called the ratio of leading coefficients. No, yes.
Wait, what happened to the 5?
Which 5?
The 5 in the denominator?
It goes off to 0 because it's 5 over x cubed.
Okay.
So the x cubed is going to infinity and the 5 is just staying 5. It's going to go off to 0. Now, as I said, you don't have to show this because, I mean, it's true and that's why it works, but as far as I'm concerned, it's a waste of time to actually spend time writing it out. But these last three examples, the bottom heavy, the top heavy, the ratio of leading coefficients, that is actually our first special technique. So this leads to our first special technique. So it turns out those last three examples just represented pretty much all cases that could happen in a limit like this. So let's say P of x and Q of x are polynomials. Then it turns out if you're looking at anything that looks remotely like this, or anything that looks like this, first thing I want you to notice, it is a limit at infinity. Doesn't apply otherwise. Now it could be plus or minus infinity, but it's some sort of infinity. Now if I take the ratio of two polynomials, like you'll notice that the last three examples is what that looks like. One polynomial divided by another. It turns out that there are only three possibilities. There is only, this will turn out in one of three ways. Now the first way it can turn out is that the answer is going to be 0. When is the answer 0? The answer will be 0 if the degree of p, now the degree of a polynomial is just the highest power. So if the degree of p is smaller than the degree of q, in other words, the highest power is on the bottom. Whenever the highest power is on the bottom, such a limit, whether you're going to plus or minus infinity, will go to 0. We call this bottom heavy. So if you see a limit like that, you can just write down it's 0 because it's bottom heavy, and like, okay, good. The second scenario, the second thing that could happen, it can go to a plus or minus infinity. Now you're going to have to pay attention to know whether you choose the plus or the minus, but it's going to be infinite if the highest power on the top is bigger than the highest power on the bottom. Call this top heavy. And of course, the caveat for this one is you need to watch the signs, right? Take note of when you're dividing a positive by a negative, or negative by a positive, negative by a negative, positive by a positive, vice versa. Watch the signs, right? They are going to determine which infinity you take. So F was case 1, right? The highest power is on the bottom, so that's just a 0, it's bottom heavy. G is case 2, so you know it's going to be some infinity, but is it plus or minus infinity? Well, you just check. Well, if I take a negative infinity, raise it to the 5th, it stays negative, multiply by a negative 6, now it's positive. In the denominator, if I cube it, it's negative, so it's a positive divided by a negative, so it's negative infinity. Negative infinity was the answer, right? So you have to watch the signs, and that will tell you what sign infinity you should take. So that's the second case. And the third case is it will go to the leading coefficient of p divided by the leading coefficient of q. That happens if the highest power is the same in the top and the bottom. If the degree of p is equal to the degree of q, you will have that. And we call that the ratio of leading coefficients. So in the last one, if you look at that, you can see, oh, this is a limit going off to infinity. Looks very complicated, so I'm probably not even going to try the first few steps. It's two polynomials, and if I look in the top, highest power is an x cubed, look in the bottom, highest power is also an x cubed. The degrees are the same, goes to the ratio of leading coefficients. 17 divided by minus 2 is going to be the answer. So like for f, g, and h, these are things where you can look at the thing and know the answer. You should be able to do that. And as far as you explaining how you got the answer, it's okay for you to write down those key phrases. So I know it's 0 because it's bottom heavy, or I know it's negative infinity because it's top heavy. Or I know it's 17 over minus 2 because it's ratio of leading coefficients. Okay? So you use these key phrases and I'll know that you know what you're talking about. But other than that, you can look at these guys and tell. So that's a special technique. So more or less, that is one of the things that you can fill into step 3. So remember when you're finding a random limit, step 1, try to plug in. If it works out, great. If it doesn't, step 2, try to simplify so you can plug in. Works out, great. Doesn't, step 3, apply a special technique. If you see any one of these guys or anything similar, hey, I have a special technique for that. I can figure that out. Step 4, if you don't have a special technique, what does the graph look like? Can I plug in some values and see what's going on? Right? And step 5 is to just notice the different kinds of functions that are involved. Like I mentioned, if we had the situation where it was like a limit as x approaches infinity of 2 plus e to the x over 3 minus x to the 1000, right? Then you should know that that's negative infinity. Again, because that's top heavy. Right? The exponential is overwhelming the polynomial. Right? E to the x is going to be larger than any polynomial. So you can kind of use this idea more generally without polynomials, but it just requires you knowing how the different functions relate to each other. Logarithms are smaller than polynomials, those are smaller than exponentials, those are smaller. So just knowing who's the bigger, badder guy as you're going off to infinity can go a long way to help you figure out what these limits are. Any questions about the process or any specific thing you went over? That's what I wanted to cover today. Just make sure you know how to do limits. So on Tuesday, you'll have a quiz on this stuff, everything you did this week. So hopefully this cleared up any misconceptions or issues you had. And this next week will go swimmingly. So then, have a good week. See you guys.